In this video, we're going to look at examples of reflections, projections, and rotations. And we're going to find standard matrices for each of those. So in this example, we're going to look at this, we're going to find the standard matrix for a transformation T going from R2 to R2, where T reflects through the X1 axis. So we know the standard matrix A is T of E1, T of E2, where T of X equals AX. So we just have to look at what E1 does and E2, and the matrix is going to be T of that E1 and that E2. Since we're reflecting through the X1 axis, which means that here's X1 on each one of those, that T of E1 is going to stay the same. That's where E1 is going to go. But E2 is going to flip across the E2 axis. So T of E1, so this is going to be T of E2 actually. It's going to be 0, -1. And T of E1, I guess I'll get rid of that there and put it up here, is going to be still 1, 0. So that would be the matrix. 1, 0, 0, -1. See if you, that's part A, can figure out, pause it, see if you could figure out part B, the X2 axis. We'll call this standard matrix B, and it's going to be -1, 0, 0, 1. Hopefully you got that answer. If you did not, here it is. You can also do a little shortcut on this. Instead of doing 2, you can say, okay, now we're going to reflect along the X2 axis, and X2 is right there. So T of E1 is going to be right there. T of E1 is going to be -1, 0. T of E2 will stay the same because if you reflect something along the x-axis, so again, here's the x2 axis reflected along, it would be that one, like a big mirror, and this one would stay the same. So that would be the T of E1, and that would be the T of E2. C, how would you do through X1 equals X2, the line? You can try that one. To do this one, we're going to reflect along, this is the line, X2 equals X1, like Y equals X. And so this one will switch to that. So here is going to be, well, let's start with this one. This one's going to switch to that. So there is going to be T of E1. What is that? That looks like 0, 1. Oops. Let me draw a line through there. Okay, and then this one is going to reflect there. So this is T of E2 now. And T of E2 is equal to 1, 0. So we'll call it C. So you start with and 1, 0. You can do a check. Let's take the point 1, 2. Let's just do a check on C. So I want to take the point 1, 2. And see if it transforms. Right, here's 1, 2. And we're going to see if it transforms to 2, 1 by multiplying by this matrix. That's what we want to check. Okay, so if I take T of X equaling Cx for this one, so in our case, so therefore, T of, call this U. So we'll call those U. So another way of saying this is if u equals 1, 2, does t of u equal to 1? So I'm going to rewrite this as t of u we know is cu instead of with x's. So therefore we have t of 1, 2 is equal to c, which is 0, 1, 1, 0, times ru, 1, 2. And let's see what we get. The first row in this column gives us 2. And then the second row, it does. There's a table in this section. If you look at table 1, it shows you the first 3 are the 3 examples that we did, reflection through x1, and these are the answer. There is more, so if you check out that table, you can practice them all. There's a reflection through x2 equals negative x1, through the origin, and others. Now let's look at the standard matrix, or find the standard matrix for the transformation R2 to R2 where t projects onto the x1 axis. So again, we're looking for the matrix A, where's t of E1, t of E2, where t of x equals ax. Okay, so all we need to do is find t of E1 and t of E2. So we want to project onto the x1 axis. So E1, we're going to take our t and we're going to leave E1 where it is, 1, 0. But we're going to take this and project it onto the x-axis. So E2 is going to become 0, 0. So our matrix A is going to be E1. Oh, sorry, these are t's. So t of E1 is 1, 0. And our t of E2 is 0, 0. That projects everything onto the x1 axis. See if you can do the x2 axis. What do you think the answer is? You can try it. Pause. Let's call it B. It's going to be 0, 0, 0, 1. Yes, that makes sense. Because if I do the shortcut way, let's do this one the shortcut way. You can do it right on the same axis. So we want to project everything to the x2 axis. So this one's already on the x2 axis. So that's just going to stay the same. This one is going to change to there. So that's going to be t of E2. Oh, sorry, 1. T of E1. So that's the first column, and this one is the second. Again, in the book, they have a table of the answers of these. So projection onto the x1 axis, that's what we did on the first one. There's the picture. Projection onto the x2 axis, that's the picture. And you can see from above, that was our answer, 0, 0, 0, 1. So you can look at these in table 4 of this section. Let's look at a 90-degree rotation. So let's find the standard matrix of T, where T is a linear transformation that rotates points about the origin through 90 degrees counterclockwise. So we know our standard matrix, again, is just T of E1, T of E2. So here is E1 and there is E2, and we're going to rotate these. I'm going to go for the shortcut method and just keep it all on one graph, but you could do two different graphs. So I'm going to take this E1 point, I'm going to rotate it 90 degrees. So this is going to become T of E1, which by the way is the point 0, 1. And then a different color, I'm going to take E2 and rotate it counterclockwise 90 degrees. So now it's going to become right there. So this would be T of E2, which looked like it's the point -1, 0. So our matrix A should be T of E1, which is just 0, 1, and then T of E2, which is -1, 0. Believe it or not, that does work. If I take a standard point, let's just try 2, 1. Let's do a check. That is the answer. So let U equal 2, 1. And if I look at T of U, we'll call it AU. Look at this. That would be A times U. What would that be? So that looks like it would be -1, right? Because this first row times this column would be 0 plus -1. And then this would be a 2. So if I take, let's do it down here. If I take the point 2, 1, and I rotate it 90 degrees, I should end up with -1, 2. Let's see if that looks right. Close. I really need grid paper, don't I? Let's make that look a little better. So I changed it to grid paper, and you can see it does look better. So here's the point 2, 1, and there's the point -1, 2, and you can clearly see that that is a 90-degree rotation. Let's do that in general. Let's rotate something through an angle in general phi by looking at example 3. So example 3 says, let T go from R2 to R2 be the transformation that rotates each point in R2 about the origin through an angle phi with a counterclockwise rotation for a positive angle. We could show geometrically that such a transformation is linear from the last section. And they show you a figure in figure 6, which I pasted here. That was in section 1.8, showing the transformation. This is the transformation, and T of U plus T of V is T of U plus V. But what we're going to do in this example is find the standard matrix for this transformation. And here's the solution. So here's E1. And this would be T of E1. And that makes sense because we know, right, there's 1, 0 rotates into cosine phi, sine phi. We know that cosine of any angle is the adjacent over the hypotenuse. And the adjacent in this case, if we make a right triangle of this, is the x value, and this is 1. So it would be x over 1. So that's why the x coordinate is just cosine of phi. And similarly, sine of phi is the opposite over hypotenuse, which is y over 1. Because this is a unit circle, 1, 0, the radius is 1. So that is T of phi 1, which is our first column of our standard matrix. The next one, T of E2, is a little harder to see. This one is E2. This would be T of E2. To see that, I'm going to take cosine of phi. But if you remember, it's the adjacent over hypotenuse. Make it a triangle here. The adjacent is the y of that angle. It's the y value over the 1. So notice how the y is cosine of phi. Sine of phi is therefore the opposite over hypotenuse, and the opposite is Well, that's an x value. In fact, it's a negative x value. So that's why they have negative sine of phi if you solve for x there. That is t of E2, which, by the way, is our second column.